So can you hear me? So it's a great pleasure to be here, and I would like to introduce the title of my presentation. It is about the discrepancy of models we all use for making estimations and also evaluations, to comparing experimental data, interpreting experimental data, and we have to question what is the use of this model. How useful is a model, for instance, if you start to build an artificial system like a prosthesis or a robot? So, and what would I like to introduce, or what I like to encourage, is that we get into a discussion after this presentation whether we have the right means of evaluating whether the tools we use are appropriate to make predictions on real systems. So the question is, if you have a system on a computer, if you have a model of your movement, is this model sufficient to build something which will then also function? And I think everybody who has built hardware will agree that usually the models we have will not function immediately if you put that into a hardware system. So the question is, what is the missing piece in the model, and can we make sure that we are going to develop better models in future which will close the gap between the simulation and hardware model? First of all, I would like to introduce my group. Last year, the dynamic walking meeting was in Jena. At this time, I already moved to a new place in Darmstadt, which is about 3 hours away from Jena. And finally, the group moved now completely since January to Jena, to Darmstadt. And Darmstadt is closely related to Frankfurt. It's just half an hour away. And the group was set up in 2003 as a young investigator group in Jena, supported by the Science Foundation. And the ultimate goal of the group was to bring together people from different disciplines. I myself, I'm a physicist. I'm working in sports science, so we have people in sports science, movement science, and now in the group we are trying to bring together engineers, physicists, mathematicians, biologists, and sports scientists in order to better understand how locomotion and motion in general is organized. And for that we use 3 different levels of research tools. We use experiments on humans and animals. We set up models, which are conceptual models or more complex models, and we are building hardware systems in order to test the models. These are some examples. At this conference, we have 3 people from the group presenting posters. I will come back to this. There will be a talk announced by Moritz. He's at the moment finishing his PhD, so he's not at the conference. This talk will be given by Shai, Rev Shai? Yeah, over there. And there are a couple people who have worked in our group during their PhD, and I'm very glad to see you all again at this meeting. So the key question of the presentation is, do we have the appropriate tools to prove the quality of our models? And the question is, if you have developed a model, you would like to build something which is benefiting of the model. So the question is, how realistic is the model? And unfortunately, in our simulation tools, we don't have the button to make this check and to say, is a model realistic or not? We would love to have it, but we don't have it. So the question is, can we close the gap, and what kind of approaches we would need to make this happen? So we have to change, of course, the models themselves. And I will give a couple of examples today what kind of changes we feel are important to be considered. And we will also use the question, like most people work and look at compliant mechanisms, which obviously are present, as we have seen in the last presentations. But what does it mean if something happens to be spring-like? Is this the stiffness? How we call that? How we deal with that? And what is the origin of it? So we would like to identify the weak points in the conceptual models. And finally, we would like to develop a methodology to better integrate biology and engineering. So let's have a look at a simple model. It was used in many presentations before, so I can briefly summarize the key properties of these 2 animations. In the first case, you have a hopping or running system, and you see that the pattern is stable even though the ground is uneven, so there is some kind of like intrinsic passive stability in the system. And Hartmut extended the model to a two-legged system, and then he showed that the same system is capable of generating not only running, but also walking gaits. So this seems to be a very convincing approach to describe human or animal locomotion. The question is it valid? So, and for that, I have selected 6 topics I would like to address in order to question the model and to make suggestions how we could improve the model. The first thing is, do we have really spring-like leg function? And I will focus on humans, but you could imagine that the same question could be also posed from animals. And we've seen animal data before, like yesterday by Monica, on the slip model. Then we will discuss to what extent it would make sense to deviate from the slip model. So what are the changes, the second order terms of the slip model which might be beneficial for movements or locomotion? Then we will discuss effects of leg masses, which are definitely something important if you build a hardware system. We will introduce the trunk and discuss an option how we can stabilize trunk movements. We will extend the model to 3D, and finally we will also discuss about the segmentation of limbs. So the first question is, do we have something like a spring in our leg? So in order to do that, we analyze data of human walking and running, and we estimate the leg function, the leg behavior, we put that into a model. And the question is now, how does this input to the model compare how the movement, the model compares to what we really do? So is the input of the leg behavior into a model really useful? So this is a setup. We have a treadmill. We measure forces and kinematics. We derive the leg stiffness, put this leg stiffness experimentally observed into the model, and question what is the outcome. This was done by Susie Lipfat, and you can find a recent paper on that in the Journal of Theoretical Biology. So this is the question: how does the kinematics compare, or the movement compares, if you follow this procedure? So these are experimental data, just examples. You can find more of these data in the thesis of Susie, which can also be bought as a book. And this is a summary of the analysis. So what you see here are forces recorded during stand space and leg displacements. Leg displacements means leg length as a distance from center of mass to center of pressure on the ground. And if you look at data in running, I think that's not surprising. You find a highly linear relationship between force and length, and this is a strong argument that there's some kind of spring-like function, at least from this level of conservation. And you also see, if you increase the speed from 0.5 to 4, it's factor 8, so the energy is increased by factor 64. You see that the stiffness does hardly change from 21 to 22. The situation in walking is slightly different. So let's have a look at preferred walking speeds, like 1 or 1.5 meters per second. There you see that there is this kind of spring-like leg function, and the values of leg stiffness are slightly higher than in running. Yes, and if you go for low speed or higher speed walking, then you observe that the spring-like operation is not found at this level of observation. So there is a discrepancy between the model and the experimental data. So if we now take the data where there is the spring-like operation into the model, we can make prediction on the movement. And this is shown here. This is a vertical displacement of center of mass. These are predicted forces and experimental forces in vertical direction and horizontal direction. And if you compare the data you got from the model and the data you experimentally observe, you see a similarity in running with some small differences, but you see significant differences in walking. And one difference is that the contacts predicted by the model with the given stiffness are shorter, and the fluctuations in force are higher. And there are several observations or reasons which could be responsible for that. These are summarized in these two graphs. So what are the differences between the model and the real lagged system? So one thing which was also described by Bullingborn and Burns in 2006 is that the foot doesn't have a point contact, so there's a shifting center of pressure, and by this there's an increased effective leg length, so there is some kind of a pivot point below the ground. Another model which was introduced by Microns in 2009 is that you can describe this by a springy foot attached to a springy leg. So we call this a foot slip model, a foot spring model. Another observation is, of course, that there is a trunk aligned attached to the leg, and this trunk has also its own dynamics. And if you consider forces, then you can see that the forces are not pointing to center of mass, but they point higher than the center of mass. And this kind of stabilizing mechanism in the trunk could also be attributing to the difference between the model and the experimental data. The second question is, we have deviation, systematic deviation from the slip model to experimental data. Would it make sense from a conceptual point of view to change leg function, to be not spring-like? I think it's from an energetic point of view, having a spring is of course very nice because you can store all the energy and you get it back. But in fact, we are not just covering movements which are energetically neutral, we also have to deal with movements where we change energy. So if you have a perturbation like a single step on the ground, like a stone, then we can operate in this conservative plane, so we can stabilize the system without introducing or changing energy. But in the case that we, for instance, go a step down, then energy changes cannot be compensated by the passive mechanics of the slip model. So these kind of perturbations cannot be handled. And we will have a very simple situation where it's becoming obvious. So if you're hopping on place and if you retract the box you're hopping on, then in the case that you would be a slip model, you would stay at the same apex height. So you would continue to hop without adapting to the changed ground level. This is obviously not what we are doing. So there is a need for compensating energy losses. And the question is, does a slip model provide a strategy to address this? So for that, Sebastian, who's also presenting a poster, has introduced a changed slip model where the parameters are continuously adapted during stance phase. So just consider that the stiffness is given at the flight phase, and during stance you increase or decrease the stiffness with a certain rate. The same holds for the rest phase. And the question is, if you deviate this parameters during stance, does it have a benefit for the stability of hopping? And this is summarized in this graph. So you see gray areas where you get periodic solutions of the system by changing leg parameters. You see that increases in stiffness and decreases in leg length, or the other way, decreasing stiffness and increasing in leg length are holding solutions, but only one part of the solution has eigenvalues smaller than 1, meaning that the perturbations will be negotiated, will be reduced over a hopping cycle. And this is something which is actually in similarity to what we observe in human locomotion, that leg stiffness does change, and that we are having decreasing leg stiffness and decreasing rest length. A third effect, which is not described in the model, is the effect of leg masses. So if you have masses in the leg, you have to consider that, and the question is, does the stabilizing effect predicted previously by the slip model is affected by it? And if so, to what extent? There was a presentation of Dio Waki at the Dynamic Walking in 2009, and they worked on a model with leg masses, and I will summarize briefly the results. So if you have a bipedal spring mass system, then you can consider its third spring, which is sitting on top of the two legs at the hip joint, which is introducing an oscillation between the both legs. And they found that there is a region of high hip stiffness and low leg stiffness where the model produced running gaits. And in contrast to that, there is another region for higher leg stiffness and reduced hip stiffness where there is a walking gait. And you remember from the experimental data that walking was indeed characterized by higher leg stiffness compared to running. So they set up a robot based on this idea where hip springs were introduced and leg springs, and they were able to show an autonomous passive dynamic running system which was able to run downhill on a treadmill. More recently, Frank investigated the mapping of the slip model by introducing masses, and he showed that there is similar behavior of stable regions even by adding leg masses in the single-legged and bipedal case of the slip model. And by introducing a hip control, by introducing energy to the hip motor, he was able to generate patterns, and he was able to introduce energy by setting a preset angle, alpha, and then the current angle was defining a certain torque depending on this coefficient K hit. And with this control, you can introduce a certain torque pattern during sense by addressing a certain reference angle where basically the spring would be at rest position. And he was considering this model with different positions of the spring as a rest or injection angle and different levels of lag dynamic. And I will summarize what he got out of the model in the following simulation. These are initially a running pattern which has a low damping ratio. Then he is switching into another running pattern which has a higher lag damping ratio and an adapted angle of energy injection. And finally, going further up to an even higher lag damping ratio, he can do a transition into a walking gate. Yesterday we've seen a presentation on the conservative slip model, which can do gate changes. Here, this model has also lag masses in the system, and it's shown that by introducing damping and hip actuation, you can manage to switch between walking gates, like here, and running gates. And this holds also for the way back, so you can run the loop very stably. The upright trunk is a problem also if you build a hardware system that you have to stabilize, and there are different options which you could use. I will here introduce a strategy which is very simple and also mechanically motivated by a simple toy, the polydoy. You know this, that you have a puppet which is completely passive, and if the center of mass is below this rotational center given by the arc, then this is stabilizing naturally. And motivated by experimental data that the intersection point of forces produced by the leg are not pointing to the mass, to the center of mass, as it would be suggested by the slip model, but to a point above the center of mass. We call this a suspension point or a virtual pivot point. And this can be nicely introduced to a model. And we did experiments on humans and also on animals, on birds and then ducks. And we saw that, especially in birds, this pivot point is also nicely established experimentally. By introducing this point to a model which has an upright trunk, we can calculate the torques required to deviate the forces to this virtual pivot point. And interestingly, these forces, or these torques, are quite resembling the forces or torques you observe at the hip joint during human walking. So the model was just assuming that there is a support point and is able to produce patterns which are similar to experimental data. So there is a nice agreement between the model and human experiments. This is illustrated in this simulation for running games. The model both for walking and for running, whereas in walking the comparison to experimental data is much better. At this conference there is a poster from Mazier tomorrow, and he extended the model also to make changes in energies. For instance, here it's presented change between forward running or hopping and hopping on place. So you can, with the help of this concept, also change speed or energy in the system. A fifth extension of the model is to go in 3D. 3D locomotion is, of course, important for the system if you would like to have it autonomous. And the question is how you position the lag in 3D. So what is the lateral lag placement, which is shown by this angle beta. There was a previous work of Justin Seyfarth, who is also here in the audience, who was addressing this by having such a lag placement with respect to a reference orientation. So just imagine you're running towards the wall and there's a goal you would like to point. Then you position the lag with respect to this orientation to the left and to the right. And he showed that this kind of strategy was not yielding to stable solutions. So Frank was slightly changing this model in order to take the velocity during locomotion as a reference base. So if you do a step, then there are slight movements of the trunk or the movement of center of mass to the left, to the right, and this is taken into account in the placement of the leg. So it's a quite small change in the strategy, so you're changing the reference frame. And by using this strategy, that you use the movement plane and you position the leg to the left, to the right, alternatively, then you can see that the region of stable running gates, in with respect to alpha, which is the angle of attack in the movement plane, and beta, the angle in the lateral side, is getting enlarged, meaning that running in 3D is actually simpler than running on a plane. And this can be summarized in a 3D graph, where you see that this intersection here, this triangle, is the area we can run in a plane. And this huge wing you see here is the extended region of stable running if you go to lateral movements. So that's a benefit of going into 3D. The last example I will just shortly name. It's a presentation also by Chris as a poster today. It's about leg segmentation, and he will address how leg joints have to be adjusted by spring in order to guarantee a spring-like operation of the overall leg. So if you're interested in that, please go to the poster of Christoph. As I promised at the beginning of the presentation, we showed different examples how the concepts can be extended, and there are many more ways of extending these conceptual models. The question remains, are we on the right track? Did we miss something? And if we miss something, how we make sure that this is being generalized or introduced into the next levels of models. And we have to clarify how we deal with the models with respect to experimental data, for human data, animal data, and experiments we can do with robots. So this is a kind of hierarchy you could set up, coming from the slip model, to go to bipedal, quadrupedal, or three-legged slip models, to slip models with leg masses. We call the T-slip model. Some people say also A-slip model for a slip model with a trunk. I frequently introduce the F-slip model, where also a foot is introduced, so you can increase this network to any extent. The question is what way we should go. So what is our navigation tool? And here are some examples that you can combine the two-slip model with leg masses and so on. This is endless. Here are two leg masses, three-leg models, and so on. So how we can approach that? And this is something I would like to invite you to join in the discussion, to make suggestions and maybe also criticize what I will propose here. So the problem is that we have conceptual models which use assumptions which might not be realizable. You cannot build the model. So we have to check whether the concept holds in reality. And of course, if you build a robot, you do that. You have the potential tool that you can validate a concept. So this is a setup we have quite now. So we do experiments with animals or humans. We set up models which have different levels of complexity, and I gave some examples of that. And we have robot testbeds. And robot testbeds are systems which you build based on the understanding you gain from the models. And now we have to introduce a methodology to deal with these three levels of research, three levels of investigation. And we call this a test trilogy. Trilogy in a way that we like to introduce a procedure to analyze and to validate the value of the concepts we derive. So I will give a simple example. Consider hopping on place, and consider the situation that you produce a model of different levels of complexity which replicates this behavior, like a single-leg model, like a slip model, or a muscle-based model, a segmented model like we've seen also before, a detailed muscle model. And the question is to which extent you have to go in the conceptual model in order to replicate the behavior. And this conceptual model can then be copied to a testbed, a robot testbed. It can be a simplified testbed like the macro hopper, where just 1 degree of freedom movements are considered, or it can be a humanoid system like the biobiped system. So, and we need a comparison of this behavior in nature, this conceptual model behavior, and the hardware testbed behavior. This is shown here in one example. You have hopping data, the ground reaction forces, and movement of center of mass. And these are different models, and the robot system is producing also a similar movement, and you can make a comparison whether the movement is similar enough in order to replicate the original movement. And it is not sufficient just to replicate the movement. For instance, the slip model is also able to replicate the force pattern we've seen in walking and running. It's also important to introduce a perturbation or a set of perturbations, which mean that we have to test how, for instance, the return map of a changed apex height to a steady state apex height is realized. And this we did in a recent study for human hopping. So these are data we got from a robot, this kind of marker hopper. These are simulation model data, and these are human data. And you see there are still discrepancies, but we hope by such a procedure that we can close the gap between the experiments, the conceptual models, and the hardware models later on. So thank you for your attention.
We have about 4 minutes for questions.
Can you speak louder, please?
Sorry, so this is sort of a synthesis as final arbiter of understanding and coding textile perspective, isn't it? Where we take physical models and use them to validate the animal experiments.
Yeah.
I worry within the context of the modeling itself that we are playing around with models without thinking about what the null hypothesis to test those models against is. And we sometimes are giving models something that are pretty fast because they are replicating behaviors that we could obtain just by observing things like the fact of launching a cycle or the fact that, broadly speaking, it's got to have the property of looking at it in certain conditions. How would you respond to sort of the difficulty of testing things within physical models being a problem and still needing something that can validate the mathematical models that we develop?
So as far as the question understood, the question is if we develop these conceptual models and if we then set up the hardware models, to what extent we can develop these conceptual models without being hypothesis driven. Yeah. So the question is to what extent we can be explorative in the mechanics when we do simulations. And I think this is one of the key insights we can get from the simulation work if we do these kind of conceptual models, that we are discovering things we would not have hypothesized before. For instance, the self-stabilizing property of the slip model, we did not expect that. We did not hypothesize what this was just an outcome of the simulation work, so we discovered it somewhere similar like somebody working in biology, if he discovers a certain animal, a certain movement there. Regarding the translation into the robot, I think, from my understanding, but this is maybe also for discussion to the audience, the key advantage of robots against animals or humans, we could compare models also with animals and human behavior, is that the robots are synthetic. So they're underlying the same concepts, they're reflecting our understanding, but they have one benefit compared to the models we use on the computer. They can only be real. There are no unrealistic robots, but there are many unrealistic models. And so this is maybe the judge we can get by the robots, that they say, okay, you're on the right track or not. The question is how we do that, how we use the robots, and what kind of measures we introduce in order to make sure that the development is navigated, that we are on the right track.
I heard a slightly different question from you, so I'd like to repeat what I heard you say, which is why the slip model as opposed to some other model. So just to say it more personally, I find it sort of offensive the status the slip model has got in some of the talks. That is, we all know the slip model fits the data, and as opposed to what? Like the slip model fits the data better than what? And it's fine for you to say, oh, we'll use it because it's predictive. That's perfectly good. But to say it's right in some sense means it's right compared to something else. And nobody's talking about what something else is or could be or what the tests are. So as a simplified model, it's an approximation that you use to make predictions and it's working pretty well, that's fine. But to say it's somehow correct, I didn't see that in your talk really, and I haven't heard it from anything interesting about that. Is that in any way repeated?
Did everybody understand what anyone said?
I think two questions in one statement. That was the other part.
Yeah. So the question from Andy is exactly what I also tried to say, but I probably did not achieve, is what are the measures? What are the measures to compare behavior? And the slip model has convincing similarities in the dynamics of the gate vectors. This is only one aspect. There's energetics, there's much, much more. And I think we have to agree on what kind of measures or comparisons we are basing our work in order to make sure that we are not sticking with one path and the other way is maybe just not seen. So it's also the question how we combine the inverted pendulum models and the slip models to a unified view. Yeah.
Or other models, or
Yeah. This is included here.
Can I just compliment Andy that in the talk that I did earlier in the session, I was actually attempting to do that in the sense of looking at slip stability to predict robust stability, looking at the demand attraction and other measures, because it does not match many of the experiments that we've seen happening. And so I did propose an alternative mechanistic hypothesis, if you will. Not to say that that's right, but it replaces slip for that particular set of experiments. I don't know if that answers your question.
We've got time for one more question.
So, might be slightly confused because we're trying to learn from animals to use our machine work. But I have a little bit of concern about spring energy conservative models, including spin model is great, give us a lot of insight. But if you go a step forward and try to use it, what if there's an evidence humans try to optimize their motion, minimizing curve? And then minimizing acceleration always makes nice smoother, minimizing force. What if our end result is a result of a complex control system, energy system model with the energy model, and it ended up being smoothest because spring mass model is the smoothest. If you do the free transform, sideways is put the minimum acceleration curve. So what if that's end up being, so you might mislead robotics, wow, spring model, let's put spring and then let's stabilize it. But that's not evidence we see it. So if you try to think about fit the transient, for example, human stabilizing from disturbance, and then what model actually fit that stability
Yeah.
concern?
So this is one of the two parts of the procedure. What I was suggesting, the question is how we understand what are the origin of spring-like behavior, and as you said, it could be that there's even no spring in the system, still the system shows for some reason spring-like behavior. So if I do this, I could do it with a rigid robot, and if I would measure leg forces, would be having a spring. So this is one example that I don't have to use springs in the system to mimic spring-like leg function. Even the leg can be at rest during this motion. So the question is, what is the methodology to identify the reason, and how we organize that? This is my question to the audience. If I would have a perfect solution, I would have said it, but I don't have it. So I appreciate this question, but I can't give an answer.
Great, thank you. Let's thank Andre for his